We're standing in the FXB building. We say FXB because it's a little bit easier than saying François-Xavier Bagnoud. This is a gentleman that graduated out of here in 1982. In 1986, he was flying helicopters during the Paris to Dakar race. Unfortunately, the helicopter he was flying malfunctioned, and he didn't survive the crash. However, his mother donated the funds to have this building built in his honor. This is the tech center. This is where the technicians have their offices. It's also where we receive all of the packages in the building, so we check everything in when it comes in. We log it in a logbook, and you have something coming in, you're going to come in, sign out in the logbook, and you're going to take your package with you when you go. We also have nuts and bolts and those type of things, so if you need anything, you're going to come to the tech center and you're going to start your quest here. So we know everybody in the building, we know everybody who does what, and we can help you get to whatever your needs are. We can help you out with those. So, this is Professor Sesnick's lab, and in here we have a large autoclave. We use that for curing carbon fiber, fiberglass, those type of composite materials. And I'm going to run you in here real quick so you can see what we have inside. So this is the autoclave. It's a large oven. You open up the door, you move your pieces inside. We can raise the temperature, or we can raise and lower the pressure. There's also electronic feed-throughs, so if you have any type of electronics equipment that you need to put in there as far as sensors on your material as it's curing. And this is used, again, for composite materials. We can run them inside of vacuum bags and those type of things inside of here to help with the curing of your samples. This is the Aerospace Learning Center. This is a nice area for students to sit with their small groups, possibly with their grad instructors. You sit in small groups in here, and you can share whatever you have going on inside of your small group. And it's just a really great place to meet. So we'll go in here. So you can see that it's set up for small groups to meet and have discussions on whatever your group is working with. And it's also a nice place to just sit and study. All right, this is the MBSE lab. This is one of 3 labs that we have at this time. And this is model-based systems engineering. And in this course, you work on projects. As you go through the semester, you'll be dealing with the chief engineers at different companies, and they will be overseeing your project. So as we go through here, we'll show you the lab itself. Okay, so on this side we have standard computers for writing proposals and those type of things, doing research. On this side there's more computers for that. This is completely reconfigurable on this side. During the semester, these computers may be removed, and this is where these different projects would be set up for working on the projects themselves. You can see things such as quad rotors up hanging on the wall over here, some fixed wing aircraft that we may use for these projects that we're working on. Everything from, rocketry, cybersecurity, just a vast number of different types of projects. And then back here, we have set up these 4 high-end computers for doing large simulations, such as finite analysis or computational fluid dynamics. And so these are all set up for doing these projects that require much higher computing capacity. If you look up on the wall, you can see all of the sponsors of this particular lab, and they supply the projects that our students are working on. And then around the conference table here, our students will sit and they will have calls with their sponsors. It could be the senior engineers. It could be the CEO of the company. We have whoever is taking care of the projects. They will speak with them on a regular basis throughout the semester, and they will have to answer those difficult questions like, why didn't you do the things we told you to do? Or even the more difficult questions like, why did you do the things we told you not to do? So this is exactly what our engineers will see on the outside when they go out into industry, and this is the foundational work that they're learning right in this class. This is the Space Institute. In this course, we teach our students how to build CubeSats, which are small satellites. We have currently 9 satellites on orbit. The ones they teach in this course are, they don't actually go into space. Most of these will just go up in the atmosphere about 100,000 feet. So we send them up on balloons. And after the balloon reaches its apogee, it will burst. And then the whole train of these CubeSats will come back to Earth on a parachute. I'm going to show you the process of that. So if you look up here, you'll see the train. So on this side, we have the balloon that will be filled with helium. The parachute, which will support the entire structure as this comes back down. These are markers so that airplanes can actually see this train as it's ascending and descending. We have radios that will send back signals so that we can track these. And then the CubeSats will be on the end of this. So we may have multiple CubeSats hanging on this train as it goes up and comes back down. So we teach the students how to build these small CubeSats. So it could be anywhere from 10 centimeters cubed to 3 times that size, which would be a 3 unit. And inside these structures that you see here will be placed all of the electronics for whatever the CubeSat is to perform. So it could be anything from data collection as far as atmospheric conditions. It could be cameras. It could be just about anything. So this is what we teach our students how to do in this course. This is Engine 100, the Aerospace Engine 100, and also Aerospace 205. And in here we teach our students how to build hovercraft, small remote control hovercraft. And they will learn all the different aspects of how to build these hovercraft. They're learning all of the engineering processes necessary for overall engineering. And this is what we teach in this course. So you want to come on in. Okay, let me grab some machines here. Okay, so these are the types of hovercraft that we have our students build. And this would be more of a, the first year, you use a motor propeller in order to create a little bit of lift. So this one's made out of a paper board. We teach all of the students how to build all of these different parts. This particular vehicle uses a motor propeller on the back with a rudder system, whereas a little more advanced system may have a motor propeller that actually rotates. So it's up to the students to come up with whatever design they want to use. But they're all controlled with the small RC remote controls. And we use this to control all the different aspects of this vehicle. So we'll race them up and down. We always have competitions of some sort, just because that's how things work out. And one of the competitions is that they're going to carry as much weight as possible. So we have these weights that we've made, and these weights will be placed on the vehicle as it goes down to the end of the atrium, our raceway, and then see how many of these they can carry back across the finish line. So whoever carries the most of these weights, that's all part of the competition. This is the 305 class. This is the instrumentation course. And somewhere around your 3rd year, you may take this course. In here, we're going to teach you how to use all of the equipment as far as the oscilloscopes, the power supplies, the function generators. We have small wind tunnels in here, so we will teach you how to use the wind tunnels. And as you learn all of the different portions in this course, you're going to apply that to the rest of your engineering from today forward. So these are small wind tunnels. They're 6 inches by 6 inches. These are one of the instruments that you'll learn to use in here. Inside here, there's all different types of instrumentation that you're going to use. This is a basic pitot-static probe, and that will allow you to calculate what the velocity of the air running through the wind tunnel is. This is also hooked up to a lot of electronic instrumentation, and all of this is actually wired up to the instrumentation on this side, and that's going to allow you to deduce what's going on here. You may interact with this, and but you're going to use the equipment on both sides of this room. Hey, this is MXL Lab, our Michigan Exploration Laboratory. And in here, we build the professional CubeSats that actually go into space. We do have 9 CubeSats that are on orbit. They were built in here. They were sent out on rockets out of either NASA. One of them went out of Kodiak, Alaska. It was on a polar orbit. And it was doing some really great work over the Arctic Circle. This is also the lab where we built the power supplies and the the power supplies and the computers for the Marco A and B CubeSats that went with InSight lander that went to Mars. So the director of that program came back here and asked that we build some of the parts for his project. And those went along with the InSight lander, brought up the telemetry and sent that telemetry back to Earth because it had landed in an orientation where we wouldn't have been able to see it. So that's how we got around that little problem they were having there. This Michigan flag was on the Orion space capsule on its inaugural flight. The flight went out 3,600 miles. And the objective of the flight was to test the heat shield. So when this came back from its 3,600-mile flight, slammed back into the atmosphere, and it proved that the Orion capsule was a fine craft. This was on board, and when the capsule returned, this was presented to us for our centennial in 2014. Okay, this is Felix Pawlowski. Felix Pawlowski was a Polish national that turned in the last century. Sometimes he went to school in Poland and sometimes in Russia. It's the same school, the border just kept moving on him. There was a lot of political upheaval in his country at the time, and he got into a little bit of political scuffle. And they put him in jail for just a short amount of time. They let him out on a technicality, but rather go back to Paris like some people would have preferred, he went down to Paris, a little town just south of Paris called Pau. And it just happened that in 1908, everybody that had anything to do with aviation showed up at this exact same spot, including one of the Wright brothers, I think it was Wilbur, and Catherine Wright, the Wright sister. And so this was the time that the Wright brothers were proving that they could fly to the rest of the world, because to this point, a lot of people really didn't believe that they could navigate an aircraft. So he has studied with all of these folks, including Chanute and Dumont and so many of the others that were down there at the time. And then after this whole time passed, he came to the United States. He was working for Packard Motor Company. And while he was working there, he talked the university into bringing aerodynamics into the curriculum. And the only issue they had was that they had nobody to teach it. So he had to finish his degree here, his engineering degree, and then he became the chair of the aerodynamics department at that time. Wasn't even called aerospace yet because that word hadn't been invented. So, but from 1914 to I believe 1949, he was the chair of the what we now know as the aerospace department today. One of the students that was here during the time of Felix Pawlowski was Clarence Kelly Johnson. You can see him here as a student working in a small wind tunnel at East Engineering on Central Campus. This was the Lockheed Electra. If you notice, if you can see in the picture here, this has only a single tail boom on this, and he proved out that this particular aircraft, this design that they had, was not stable under a certain flight regime. And he proved this out, and they went with a dual tail boom on this particular aircraft. And that was their trademark for many, many years, was multiple tail booms on the rear of the aircraft. He went on from there to work at Lockheed after he graduated, and that's when he created the Skunk Works. The Skunk Works were involved with all of the secretive aircraft, including the P-38, the F-104 Starfighter, the whole SR-71 line during the Oxcart program, right up all the way through the F-117 program that was one of our very first very stealth aircraft. And this program continues on today. Okay, this is an award that was given to General McDivitt. And General McDivitt was on Gemini 4 with Ed White. Ed White and Jim McDivitt are both alumni of the Aerospace department here at the University of Michigan. This was the day that Ed White took the very first American spacewalk. General McDivitt also went on to Apollo 9, so we flew on Apollo 9. And after he was finished with his astronaut duties, he actually headed up the human spaceflight program for NASA for many years. When he retired, they gave him this nice award, and he asked if we would display this for him. Rather than having it sit on his shelf at home collecting dust, we're able to see this. If you look inside of here, there's a very small piece of rock. This is a piece of rock they brought back from the moon. Okay, so this is the Redstone rocket. This is the rocket that took us up for our first suborbital flights. It was not powerful enough to get us into orbit, but it would take us up and back down. So the early Mercury astronauts actually flew on this. This is a retro rocket off of the SpaceX Dragon capsule, and this is used for maneuvering purposes on the capsule itself. This is a J-79 jet engine. It was used on the F-4 Phantoms and several other aircraft. But we have it opened up so you can see the compressor section. You can see that the compressor blades are adjustable. And then as the air continues through here, compression happens. The air flows through here, the compressed air, and this is where the combustors are. And then the turbine is here, and it spins up the turbine, and then there was an afterburner that actually went on the backside of this. And this is an Allison turboprop. So the jet engine on this spins up the gearbox, and then the propeller that fits on the shaft here is where we get all of the thrust out of this particular aircraft. Okay, so this is the NOMAD. This was designed and built by Professor Lesher back in the late 50s. This is a push-prop aircraft. You might notice that the propeller is in the backside of this airplane. That gives you a nice clear view out the front of the airplane. This was the first design that he came up with. This was a two-seater. The next design was the Teal, which is a single-seater. That's up at the Experimental Aircraft Association's museum in Oshkosh. And that particular aircraft, it held 7 world records. 5 of them still stand today. Okay, we're entering the wind tunnel building, where the largest wind tunnel is, our 5x7 wind tunnel. This is a scale model of the 5x7 wind tunnel. 5x7 wind tunnel refers to the test section, which is here. It's 5 feet high, 7 feet across, about 25 feet long. The entire wind tunnel is 335 feet long at the center line, so it's longer than a football field if we were to stretch this out. There's a 10-foot diameter fan that we use to move the air. That's turned by a 1,400 horsepower motor set that's located in this house out here. As the air continues around in this direction, you see that the volume increases. It gets much larger. As the volume increases, the velocity decreases. Then through the settling chamber, the air will flow through these screens, and then it contracts down into the test section. If we're running 150 miles an hour in the test section, it's only 10 miles an hour on the other side of the wall here, and that makes it a 15-to-1 contraction. Okay, so this is the test section for the 5x7 wind tunnel. Down below the test section, we have a balance. This balance will pick up all of the forces that will be placed on the model that's inside of the tunnel. So we'll mount our model inside the tunnel. As the air flows around it, we'll get lift, drag, side force, and all of the moments. And again, that will be picked up by the instrumentation down below. This balance system was designed and built by Professor Lesher, who built the little aircraft that we were just looking at a few minutes ago. He designed this in 1947, built it in 1956, and it's still working beautifully today. This is a 2-inch by 2-inch supersonic wind tunnel. We use this for instructional purposes to teach our students about the development of shock waves on the front of vehicles. If you look inside, you can see that there's a wedge in here. There's two different shaped wedges. They're cut at different angles. So the shock wave is not dependent on the angle of the vehicle itself. It's more the velocity that it's running up against the wind. So in order to run this, we have, on the other side of this wall, we have 9 railroad tanker cars. They're currently pumped down to about 26 inches of mercury, and that will allow us to attain speeds of Mach 2, somewhere in that range. So by opening up this valve, the air rushing, the higher pressure air in this room rushing to fill the vacuum tanks is what we're going to use to power the supersonic wind tunnel. And right now there's a shock wave set up on the front of the model. We use high intensity light sources. And turn it off. We use a high intensity light source, and when it projects over on the screen behind you, you can actually see the shock wave on the front of this model. Okay, so this is the model that we're using inside of the tunnel. You can see that there are 2 different angled cuts on the front of this, our vehicle, as it were. With the air traveling this way, you can see the bow wave coming off the front of this. If you were standing right here, you wouldn't hear this vehicle passing you until the shock wave reached your location, and that is known as the sonic boom. So it's this pressure wave coming off of here, and that's what we're looking at with the supersonic wind tunnel. You can see some secondary shock waves coming off these other angles here, and it shows up a little bit darker in this photograph.